It's lecture 5 for week 14 of CS 1030. In this lecture segment, we're going to keep talking about real computers, and remember that we'll get back to Java next week. So let's talk about memory. So one of the things we want for the main memory on a computer is that it should be as fast as possible, and it should also be cheap. And we kind of, unfortunately, have to choose between those. It turns out that you can make memory pretty huge, and you can also make it extremely fast, but we have no idea how to do memory that's both. We just don't have the technology to make huge memories that are extremely fast. So on the other hand, we have memory that is extremely fast, like the processor registers that sit right near the CPU, or actually part of the CPU. And like I say, these are incredibly fast. They can always be accessed almost instantly, but there's very limited registers. So if you remember in the last lecture segment, we talked about how in the Intel architecture, there's only 16 general purpose registers. And so 16, 32 or 64-bit quantities. And so that's not nearly as much storage as we want. Remember, we want billions and billions of times more memory than that. So the question is, how can we get memory that's nearly as fast effectively as registers, but nearly as large as, or this as large as the memories that we buy? And it turns out that there's a very clever way to do this, and it's called caching. So what a cache is a small amount of memory that's very fast, and what it does is it only stores some of the contents of the main memory, of the much larger main memory. And the reason you can make this work is that it's most often the case that a computer is only using a very small part of its memory at any given time. And so what the cache does is it sort of automatically copies some of the memory that the computer is using into this smaller, faster memory. And then if you start using a different part of the memory on the computer, then it just caches that instead. So it's basically like a temporary copy of a much larger memory. And because of this property, we call it the locality property, that we often use sort of only a small amount of memory at any given time, this caching scheme works. And it turns out it works so well that we often have multiple levels of cache. There's often what we call a level 1 cache that's fairly small and very close to the CPU, a larger level 2 cache, an even larger level 3 cache, and then there's the main memory, which is not a cache, it's the actual thing. So what we end up getting is sort of a hierarchy, and the hierarchy shown here contains more than just the cache and memory hierarchy, and I'll sort of explain this as we go. So at the top of the hierarchy, we have a small amount of very fast storage in the processor register file. So here, for example, we might have only 16 registers. Then we have multiple levels of cache. We have the L1, or the level 1 cache, level 2 cache, level 3 cache, and as we go down the hierarchy, these are getting larger and slower, and that's sort of what the widening of the triangle is intending to show. Then once we've, below that, we have the random access memory, the main memory of the processor, and this is the thing that you would, on a computer that you buy from the store, have 16 or 32 or 8 gigabytes of. And then we can sort of keep going. So one of the tricks that we'll learn about when you take operating systems, or if you take operating systems, is that the hard drive or the solid state disk on your machine can be basically viewed as an extension of the memory, sort of an even bigger memory. And in this view of things, the physical memory on your machine, the RAM on your machine that you have 8 gigabytes of or whatever, that can be viewed as just a cache for the hard disk. And it's kind of a sort of an interesting scheme, and this is sort of built by the operating system, and we're not going to sort of go into it. But what we get is this very interesting big hierarchy of storage spanning many orders of magnitude. And we can look at this sort of in a different way. So the CPU registers we can usually access in less than a nanosecond. So, more than 1 billion times per second. The cache RAM in the different levels of the cache is generally going to take some small number of nanoseconds. Dynamic RAM, and so if you remember, we talked about static RAM and dynamic RAM, I don't know, maybe 6 weeks ago. These are the two technologies at play here. The DRAM, or dynamic RAM, is the very large memory that you might have, 16 gigabytes of. That takes, sort of a substantial number of nanoseconds to access. So it's much, much, much slower than the registers. And then things like magnetic disk or SSD can take sort of up to microseconds or milliseconds to access. And so these are even hundreds or thousands or millions of times slower than the dynamic RAM, which is itself much slower than the registers. So you get this sort of very large number of orders of magnitude of differences in size and speed. And getting this all to play together is sort of an interesting design challenge for computer designers. So how do we measure the performance of a modern CPU? So here over on the right, we've shown a modern CPU, and it's a little bit of an atypical one because it has 3 cores. You can see there's 3 CPUs. Mostly often we see power of 2 number of cores, although not always. And one of the things that was sort of interesting here is we can see the level 2 cache here. So the level 1 cache is per CPU, and the level 2 cache is shared across cores on the same chip. And this particular chip doesn't have any level 3 cache. So how do we measure the speed of this? Well, usually we talk about the clock speed. And so remember that your simple computers have a clock. For simple computer 1 and 2, you are the clock. So your computer is running at at the very most a couple of cycles per second. And for simple computer 4, the more automated one, then this one you could clock automatically, and this one you could clock up to many hertz if you want to. So let's talk about clocks a little bit. So all the clock is a wire that goes from 0 to 1 and 1 to 0. It just oscillates between the two binary values at a fixed rate. And so you can think of it as a metronome. So if you ever took piano lessons or something, you remember that there's a metronome to kind of keep you, you can use a metronome to keep you on time for the piece you're playing. The clock for the chip is basically like a metronome, but it's going, maybe a billion times a second. And so we measure the rate of a clock in cycles per second. And that 1 cycle per second is 1 hertz, or Hz is the abbreviation. And of course, modern computers run at something like 2 to 4.5 gigahertz maybe. So 2 to 4.5 billion cycles per second. So they go very, very fast indeed. And then another thing we should sort of look at a little bit is how modern computers are multi-cores. So here's an Intel Core i5, which has 4 cores on it. So the big thing here, the big multicolored thing, is the piece of silicon manufactured by some Intel foundry that gets packaged up inside of a larger die, and that's the thing you buy and plug into your motherboard. And what does this piece of silicon have on it? Well, it has 4 CPU cores. The CPU core is an ALU and a memory interface module, and probably some level 1 cache and some other stuff. It's just got sort of, all the stuff, the decoder and all these other different pieces of logic. Then there's a shared level 3 cache. So I guess that means there must be level 2 cache must be per core on this particular chip. So the shared level 3 cache, which is quite large here, it might be several megabytes. There's a memory controller. So this is the interface for talking to the main DRAM, which of course is located off die. The DRAM modules are located, in separate DIMMs that are loaded onto the motherboard separately. And then besides the cores, the cache, the memory controller, there's some external logic on the outside for interfacing with devices. And remember that, interfacing with video cards and sound cards and other things like that is sort of a really key part of what your computer does. So there tends to be quite a bit of circuitry devoted to interfacing with that stuff. So something that's happened with cores recently, and sort of, just over the last decade and a half, is that most of the common computers that you would buy have moved from being a 32-bit architecture to a 64-bit architecture. And so let's talk about what that means in terms of the simple computer. So the simple computer was what we call an 8-bit architecture. And the reason we can know it's an 8-bit architecture is because registers contain 8 bits and instructions that are loaded are 8 bits. So we might also expect memory addresses to be 8 bits, but they're not. They're only 5 bits on a simple computer. But still, it would probably best be understood as an 8-bit architecture because that's the size of the registers. So in the 32-bit architecture, the main processor registers are 32 bits, and in the 64-bit architecture, they're 64 bits. And it tends to usually be the case that the size of a memory address on the computer is the same size as a register. And although that's not the case on a simple computer, and that hasn't been the case on many computers that have been designed, but it often is the case. And it is the case on Intel CPUs. So what that means is on a 32-bit Intel machine, you have memory addresses being 32 bits. So you can address at most 2 to 32 different things. And the things that you address are bytes. Remember that we're always dealing with byte addressable memories. So you can address 2 to the 32 or about 4 gigabytes of memory. On a 64-bit machine, the registers are each 64 bits big. And now memory addresses are 64 bits. So you can address, I don't have a good word for the amount of memory that is, but it's a lot. No particular single computer ever manufactured has had an amount of RAM that you would need all 64 bits to address. It's just a very large amount of memory. So one thing we should talk about here, and this is sort of, gets a little complicated, but this is sort of something that's I think really, really important for students to understand, is how long different things take using your computer. So here's a chart I've loaded up. It's from 2012, but these numbers haven't changed that much, so it doesn't matter. And this shows how long different things take. So level 1 cache reference. So if you talk to the level 1 cache on your processor, your chip on your laptop or your phone can probably do that in about half a nanosecond. Or another way to say that is, you can probably do that about 2 billion times per second. So we'll skip over a few of these things, and now let's look at the main memory reference. So a main memory reference might take 100 nanoseconds. So you can see that accessing the DRAM is about 200 times slower than accessing the level 1 cache. So you can see that we really want to avoid DRAM references through our main computation, because otherwise our main processor is going to be mostly stopped just waiting for DRAM for a lot of different, for maybe 300 or 400 cycles if it's a 4 gigahertz processor, and it's not doing any useful work while it's waiting. So something like reading a 4 kilobyte chunk off of your solid state disk, off the SSD, that takes 150,000 nanoseconds or 150 microseconds. You can see that this is sort of a lot slower even than talking to main memory. Something like a seek on a spinning magnetic disk, which we're seeing less and less of, but they're still in many computers. A disk seek on a spinning hard drive takes 10 million nanoseconds or 10 milliseconds. So you can only do that 100 times a second, whereas these other things you could do 2 billion times a second. So the orders of magnitude are sort of, there's a lot of orders of magnitude of difference here between different things. And the reason this is important for you is when you're writing computer programs, they tend to do these things, right? They ask for the disk to seek somewhere. They talk to main memory. They do things that are equivalent to looking into the level 1 cache. You're actually doing these things. And if you don't know how fast they are, if you don't know the relative performance of these different things, then it makes it hard to write code that's fast. It's easy to write code if you don't understand how long things take that's really slow, because it's going to do slow things too many times. And so a lot of designing fast computer systems boils down to doing these things, doing lots of fast things instead of doing lots of slow things. And a lot of sort of cleverness goes into this. So nanoseconds are pretty abstract, right? Nanoseconds are kind of hard to understand because they're so small. So in the final slide in this segment and in this week, we'll look at sort of a human scale version of this. So let's say that, for example, we made a computer 1 billion times slower. So if we made it 1 billion times slower, now a level 1 cache reference, instead of taking half of a nanosecond, takes half of a second. So about maybe on the same order as a heartbeat. So in this case, a main memory reference now takes 100 seconds. So this is as long as maybe it takes to brush your teeth or do some other sort of short task. Okay, so if you slow down the computer 1 billion times, a clock cycle on your computer is a fraction of a second. Just talking to the DRAM, to the main memory once, is 100 seconds. And if you remember, the simple computer didn't work like this. On the simple computer, the DRAM or the main memory worked just as fast as the ALU. There wasn't this speed difference. And that's something that you can do if you're making very small chips that don't have a lot of memory. But once you start having many, many, many gigabytes of memory, then suddenly the speed difference appears. And you can see that, so now it's the difference between a fraction of a second and brushing your teeth. So if we read from a solid state disk, and remember SSDs, these are the fast disks on your computer. A read from that takes 1.7 days now in this new sort of slowed down by 1 billion times computer world. So that's really slow. And so you ask yourself, should I read something from the disk, or should I do some computation where I could maybe figure out the same thing that I would have loaded from disk? Well, you can do computations in a fraction of a second, and reading from disk takes 1.7 days. A disk seek on a spinning magnetic disk on a hard drive now takes 16.5 weeks. So something like a semester at the university. So it becomes really, really slow to talk to the disk. So you can see that fast computer programs really, really, really need to avoid talking to the disk at all costs if they don't want to, become slow computer programs. Anyway, so this is a chart you can find online. You can find the other one there too. And I would encourage you to sort of think about this and start to get to know these numbers, because there's sort of an important part of understanding how things work and how they all fit together.